So welcome everybody. I'm sorry that we cannot meet in person, but I hope this will be more or less effective. Feel free to interrupt me if you have some questions. So I am going to talk today about the perception component for autonomous driving, both for single vehicle autonomy, but also sort of more general scene understanding and situation assessment, which is required for the decision-making and control in the context of autonomous driving. And my tutorial has two parts. So in the first part, I'm going to follow up on some of the techniques which Frank talked about, in particular, application of different machine learning techniques to different perception problems. And in the first part, I'm going to focus only on the 2D perception and discuss different kind of models and data sets. And then in the second part, which will be tomorrow, I will continue with kind of 3D and then more the connection to control. So what is perception and what do we mean by perception in the context of autonomous driving? So it does not come as a surprise that sort of we can build better autonomous vehicles if we have sort of better mechanisms of being able to aware of our environments, and this can then further guide our decisions. So there are a lot of aspects to perception which are relevant to this problem. And there are also a lot of sensing modalities. So we are going to be looking at problems which require typically multiple sensing modalities. And the idea of perception is to take this raw sensory information and come up with some useful representation of surrounding environment. So the first few examples of these useful representations which we have on these pictures are, for example, given an image, being able to figure out what are the drivable areas and what are the lanes, what are the exact lane markings, where are obstacles, which areas are occluded. Then in the bottom part, we, for example, have some information where are the additional vehicles. We can potentially estimate their location, estimate their speed, how they're moving. So you can imagine that being able to understand what are the other traffic participants and being able to extract this information directly from images, it's sort of very useful. And here we have examples not only of the vehicles, but also, say, bicyclists, pedestrians, other traffic participants, which are possibly dynamic and moving, but we also may be interested or are interested, for example, to figuring out where the traffic lights are, where are different traffic signs, because that can also affect the strategies for decision-making and control. So this information on the first slide is typically kind of relevant for kind of this online decision-making, which has to happen on board of autonomous vehicles. And then we have the other type of sensing requirement where sensing also comes in place. And these are sort of these aspects related to mapping and localizations, which are both relevant to an online decision-making, but also for map building. So we already know that the current models and maps which support the algorithms and techniques which are running on board of these vehicles rely heavily on the availability of the maps. So having this ability of being precisely and exactly localized where you're on the map is also where the perception plays some role. And this can be also achieved using either visual sensing or using different range sensing modalities. So this is just to sort of give you a kind of a quick snapshot what are possible sensors the autonomous vehicle can have. So current autonomous vehicles are typically equipped with a variety of sensors, including cameras, LiDAR, radar, ultrasound, and many of these cameras have different field of views, different resolutions. which then sort of affect what part of the surrounding environment is being sensed. So the picture on the right is an example of the sensing suite of Tesla Autopilot, where for Tesla, there is majority of sensing emphasis is on visual sensing, but they also have sort of LiDAR and radar sensing. So in the first part of this tutorial, I'm going to primarily focus on visual sensing because it's sort of frequently used modality in the context of many of these platforms. And this is also kind of a good vehicle to introduce some of these machine learning models. And then I'll discuss how some of these things can be extended to range sensors and LiDARs, and how we can build useful representations of these environments, surrounding environments, from these other sensing modalities, and also how we can combine visual and range sensing to build this in the context of particular class of learning frameworks. So this is sort of a little bit of a preview. As I mentioned, I will start with kind of a brief recap of these deep convolutional neural networks. And I think Frank already covered many of these aspects in the previous tutorials, but I will review a little bit and discuss some aspects which are related to the architecture choices and how one goes about making various trade-offs, because as you can imagine, this field is quite overwhelming. There are a lot of possible choices and alternatives which are being explored. And I think understanding some of these trade-offs or rationale behind these choices could be helpful as one is kind of deciding on how to proceed or understand what the different alternatives offer. And so in the context of these deep convolutional neural networks today, I will cover 3 problems. The first one is the image classification, and I'll just use it to introduce different choices of architectures. And then I'll continue with the problem of object detection and semantic segmentation. So we will go to sort of hopefully the right level of details when it comes to this sort of nitty-gritty choices one has to make when deciding on the right type of model. And then tomorrow I will continue with models which are commonly used for obtaining 3D representations, which help us understand the motion and tracking and help us sort of reason a little bit more about traffic participants, which can then sort of further guide models which can do better prediction and also overall scene understanding. And then tomorrow I will finish with some examples of how to integrate these models of perceptions in the control loops of the systems and the decision making. So if we take the sort of the basic vanilla neural network, which one typically encounters in the first neural network class, you typically see a fully connected network which has some number of layers. And Frank already sort of elaborated why having more layers is better and so forth. And so when it comes to visual perception, where the input is an image, it's very useful to consider a particular class of neural networks which explore the spatial structure of the image. So just to sort of contrast some of the alternatives. So if I were to design a fully connected neural network for image classification, if I would, for example, give as an input an image, if the image is 20 by 20, I would have to unstack that image into a 400-dimensional vector, and that would be an input to my deep network, followed by some number of fully connected hidden layers. And then the final layer would be some softmax layer, which would give me some prediction whether this image belongs to one of the sort of predefined classes. So if you see this type of architectures do not really consider the fact that the neighboring pixels in the image are actually related because they are spatially close, and likely the weights which are related, which are sort of combining the neighboring pixels, should be somehow related. So instead of considering an image as this kind of vector of numbers, sort of a while back, there was this concept of the so-called convolutional neural networks, which exploits this idea of the spatial neighborhoods in the image, where instead of with the fully convolutional, fully connected neural networks, each pixel is independent and it's connected to all nodes of the hidden layer. In convolutional neural networks, we are considering the weights which are applied to the spatial neighborhoods of an image, where the size of the spatial neighborhood is a parameter. And these weights are then applied across the image in some sort of sliding manner, such that the final result of multiplying an input image with the set of weights would be sort of correspond to the operation of the convolution of an image with the filter. So if I apply this filter to a single image, what I'm going to get is I'm going to get a particular feature map, where that feature map is simply has a per pixel response to that filter at a particular location. And so you can imagine that if one sort of designs or sets up an architecture with multiple of these filters, one can then attain multiple of these feature maps. So here is, so this is sort of the main idea behind this convolutional neural networks, that you can think of the weights as being the parameters of the filters which the image is being convolved. And there is sort of a big history in image processing and computer vision, which sort of tries to come up with the different filter bases which capture different patterns in the images. And so here, the idea is that in our case, instead of considering some pre-designed filters with some sort of engineered filter bank, we'll have an ability to learn the weights of the filters in a way which fits best the data set and the problem at hand. So this was sort of one of the most, I guess, insightful and effective mechanism, which really dramatically improve the performance on these classes of problem. So I want to just kind of provide some conceptual view of this convolutional neural network, because we're going to be using them throughout the these two tutorials. So the way how you can think about it is that you start with an image, and in this case, suppose that I have 21 times 21 image, and we can, in this simple example, we can imagine that we just have a single channel, so it's just a gray level image. And the first layer in this toy example would correspond to the 4 feature maps, which would mean that I'm going to learn coefficients of 4 filters, where the size of the filter, if the filter is 3 by 3, I'm going to learn 9 weights for the filter, and convolution of that image with that filter is going to generate a feature map, which is going to be the same size of the image. So notice that as I sort of go down the layers, I'm generating feature maps with increased number of channels. And another operation which is happening is some kind of pooling and nonlinearity, which is then reducing the resolution of the feature maps And Frank already discussed the different versions of these poolings. And so you keep on doing it, stacking layers and layers after each other. And then at some point in sort of the early architectures, this was followed by some fully connected layer where you simply would unstack all these feature maps into long big vector followed by a couple fully connected layers. So at the level of single layer architecture, what we can think of is that these convolutional neural networks, one layer has some set of filters which are applied to an input image, followed by nonlinearity and followed by pooling. And these layers are then repeated into forming deeper and deeper architectures. So these convolutional neural networks, this idea of sharing the weights across different parts of image, and also this filter analogy has been introduced some time ago. So in 1998, these classes of models have been applied to US postal digit classification, where we would have problems. This was introduced by Jan LeCun, and the scale of the problem was the images were of the size about 30 by 32 pixels. And as you can see, the network here had 1, 2, 3, 4 of these convolutional layers. So what happened is that sort of feature maps of increasing size in terms of number of channels, but the reduced resolutions, 4 layers like this had been computed, followed by, I believe, 2 or 3 fully connected layers. And this was really, so the limitation at that time were to a large extent due to the size of the data sets which were available in order to train these networks versus the number of parameters the network had to learn effectively, and also the time it took to train the network. So what has happened, so this was a little bit of a history, but what has happened since is that in computer vision, there has been sort of certain culture adopted, that a lot of benchmarks have been developed in order to sort of understand the performance of different representation and techniques for classification and detection. And at some point, the size of these data sets kept on growing. And one of the largest data sets, which came around 2011, was this ImageNet data set, which was a data set which was comprised of 14 million images and 20,000 classes. And these were typically images gathered from internet, where the labels, you would have a single label per image. The label would be one of the 20,000 categories of objects. And this was really the availability of this data, and also the increase in the computing power and the availability of graphical GPUs sort of created this kind of perfect storm, or the breakpoint in being able to actually design and train these deep convolutional neural networks, which had much larger size and depth than the ones which were initially introduced on this MNIST digit classification. And so what has happened is that that first introduction of this deep neural networks suddenly marked a dramatic improvement in the performance of, I'm sorry about that. Do you see my mouse when I'm clicking? Okay, so let me try here. So mark the dramatic, can you see my mouse?
Yes.
Okay, good. So notice that, sorry. So before, the performance was in kind of 30s on this big image classification net. And the big drop was marked at the time where this deep deep network was introduced. Sorry, I'm trying to fix this. So one of the first deep networks was, which was introduced, was simply the variation of the network proposed by LeCun, but with larger number of layers. I think there were about 8 layers, and it was possible to train it due to the fact that there was almost 1 million images available for training, because there was a large number of images with labels which could provide the signal for the backpropagation, and it took about 1 week to train this. So what we're going to discuss a little bit, some of the advancements and ideas which have been introduced since this first attempt to apply some of these techniques to really real-world images and data, and also trying to get some better understanding what these models learned. So after the network was trained, there has been a lot of effort devoted of trying to understand what these neural networks learn. And a lot of visualization tools have been developed, which enabled us to sort of interpret a little bit the representation learned by the networks. So at the early layers, at the first layers, it's very easy to interpret what the network is learning, because we simply have the weights of the filters which were learned, and these weights can be simply visualized as filters. And then in the first top left picture, these are depicted as images. So, however, if you move further down the network and look at the other layers, we have, at individual layers, we have several feature channels. So in order to try to understand what type of representations these feature channels are learned, people have developed some techniques how to actually look at neurons or areas with high activations, and then go and backtrack and try to figure out which parts of the image cause these areas of high activations. And so here are some examples on how the top 9 patches at the layer 1 look like. So these are, what are the top 9 patches of the particular high activation weights in layer 1 looks like. And you can see that the patterns which are being learned are much more complex than the simpler, vertical, horizontal, diagonal filters, or some kind of line filters or corners, but they have more complicated patterns with different levels of shadings and colors and so forth. And if you then move further up the layers, the neurons now have a bigger receptive field. So the representation which they learn actually comes from a bigger part of an image. And so you can see that already at the layer 3, some semantic concepts emerge. So you, for example, have some weights which respond to foreheads and faces, and then you have some textures or patterns, then you have beaks and noses. So some of these patterns which repeat frequently in the data set are sort of being locked on by some parts of these networks. So this is just sort of a little bit of an intuition what kind of representations are being learned here. So this was sort of quite insightful, and people have sort of noticed that these networks can learn very effective representations and essentially sort of take away that very laborious part of the process of designing the right kind of features to extract from the raw sensory measurements in order to guarantee the right type of invariances in order to achieve a particular classification tasks. And so this was immediately very effective in computer vision, but this idea of learning the features was also then later extended to other sensing modalities, where the choice of features or hand engineering features was no longer so obvious as it was in computer vision, where we had sort of a lot of history of studying of right kind of feature representations. So let me kind of clearly define the three tasks, and we'll discuss the main architectures which are being used to tackle these tasks. So the first task is the very kind of basic task of image classification, where you have the main image, one image, and each image has a label, and you are tasked to train a deep convolutional neural network in order to classify, to maximize the classification accuracy on a particular data set. So this is the basic variation of the task proposed initially by Jan LeCun on the MNIST classification. The only thing which is going to vary are the data sets and the labels which we have. And we're going to start with this task, and then we'll continue looking at the detection and semantic segmentation problems, which are more detailed predictions. So the first type of prediction task is just trying to predict the label. So what has happened since the original MNIST? Well, so the main advancements which have been made were in evolutions of the architecture of the deep convolutional neural network, and I'll discuss some main ideas behind this evolution. So as I mentioned, the very first architecture was this AlexNet, which was the network which won the first ImageNet challenge and improved the performance by a significant margin. And that initial architecture was simply just the variation of the architecture of Jan LeCun, just with increased number of layers and the ability of handling high resolution images. But since then, we had many other developments. So there are sort of these ideas of network and network architectures, where instead of using the simple convolutions, you have some nonlinear neural networks being applied to local spatial neighborhood in the image. There were lots of advancements in increasing the depth of the network with the hope of sort of improving again the performance and the type of invariances. And this sort of came along with advances in optimization techniques, because as you already probably discussed in the previous lectures, the deeper the network is, the backpropagation algorithm typically encounters some problem of so-called vanishing gradients. So the gradients become smaller and smaller and smaller. And towards the beginning of the network, there is not enough signal to do the weight changing. So these sort of technical aspects have been also accommodated by the changes in the architectures. And then, you know, as sort of the time progressed in this period of 5-6 years after the initial success, the networks became deeper and also more efficient. So let me kind of discuss just a couple ideas which were driving the evolution of these architectures. And so now, in order to kind of think how these different things evolved, I'm gonna just represent the individual architectures in terms of some blocks, where the dark blue box are simply convolutional layers. So those are the layers which generate the feature maps. Then the red little slices are some nonlinearities. So this can be some rectified linear units most frequently, because they have been shown to be the most effective when it comes to performance and training. And then the dark gray areas are the pooling layers. So one class of, so this is, sorry, I have one slide behind. So here is sort of a simple comparison, and a lot of these observations have been sort of obtained with this motivation of choosing the right function, assuming that sort of taking the stance that these neural networks implement just some function, right class of functions which will sort of fit the data sets which we were optimizing on in order, and these data sets usually had quite large diversity such that these initial architectures then were also successfully applied to other kinds of problems. So the first observation which was made in these early changes in the architectures is that it is, the networks were developed with denser stride. So instead of obtaining the output at every fourth pixel, the output of the convolution was obtained at every second pixel. And the other kind of qualitative change which was made is that it turns out that if you are convolving an image with the filter of a larger size, this is equivalent with the two consecutive convolutions of a filter with the smaller sizes. So notice that here, many of these, so the first component was mostly related to the stride and having simply denser padding. And in the second improvement, the main change was this idea of using the many small filters applied consecutively, and that was sort of shown to be equivalent to using a larger filter, but with the advantage of having smaller number of parameters. So here is kind of a transition from this Ziegler-Fergus net, which was the sort of the follow-up of the AlexNet, suggesting kind of a smaller padding and deeper layers, to the so-called VGG net, which comes from this very deep convolutional neural network paper, where the depth of the network increased significantly. And notice that the sizes of the filters are all very small. So all the convolutions are simply 3x3 convolutions, but because they are applied one after another, the effect is the same as if we were applying a convolution with larger filters. And again, at the end, these networks were followed by some linear layers, linear fully connected layers, where at the end, the output of the last convolutional feature maps was unstacked and connected to the fully connected layers. So this was the idea of small filters, but many of them, and having bigger depth. And these architectures, of course, came with their own strategies with training. They were typically trained in multiple stages, where at each stage, once it was pre-trained, it was frozen, and the second stage was again focused on training the consecutive levels and so forth. So the other idea which typically one encounters in these convolutional architectures is this idea of factorized convolutions. So this was motivated by this observation that instead of just using a convolution, which is just a linear operation, what if we would have some little neural network inside of the sort of individual computation on the local neighborhoods, which would have some ability to introduce some nonlinearity and presumably learn sort of more interesting concepts. So this idea of network in network was introduced in 2014. And then this was sort of further extended by considering the following kind of model of the convolution, where within the individual layer, we would have convolutions 3 by 3, followed by nonlinearity, and followed by 1 by 1 convolutions. And these 1 by 1 convolutions sort of will keep on reappearing. They're sort of very effective mechanism how to reduce the dimensionality of the feature map, both making the dimensionality lower and making the dimensionality higher. And they're simply operating on just on a single pixel and all the feature maps. And they're being basically they slide along all the locations in the image in order to come up with some new representations of the feature map. And so this idea was this network in network idea was further extended by this inception architecture, which takes it into a little sort of bigger extreme, that it introduces the so-called inception module, where within this network in network idea, the network has actually multiple paths which can take, and then these are then concatenated into the final output. And this particular individual block is called, it has 4 different paths. Some of them are just some combination of dimensionality reduction and convolution. Some of them have max pooling and 1 by 1 convolution, and some of them has just 1 by 1 convolution. And the network then has the ability to kind of figure out how to combine these different paths and come up with the right set of weights in order to, again, sort of maximize the accuracy on a data set. And so this is, again, this idea of having this single module, which is then repeated across many, many layers in order to attain a particular depth. So one interesting thing when it comes to these, there is actually, sorry about that. Let me sort of backtrack here. I don't think I have kind of a good slide for this, but one thing which some of this evolution of the architectures brought out is dramatic decrease in the number of parameters. So this last inception architecture had about 1.4 million parameters in these last layers. And so here, this is a plot which is telling you what is the number of parameters per layer. And this is the number of operations per layer. So the early layers where you have a lot of convolutions have a large number of operations, but then the later layers, the number of operations per second goes down. And this is to sort of highlight or compare it with the early architectures, which where the majority of the parameters were in the last set of fully connected layers. This was 75 million parameters, were all sort of concentrated in those last 3 fully connected layers. So some of this improvement in the architectures marked a dramatic increase in the number of parameters, without really sacrificing the accuracy in the performance, in the classification performance. So following a little bit on this kind of development of deeper and deeper networks, so one of the last networks which really sort of pushed the idea of the depth and also introduced some interesting design principles to handle the vanishing gradient problems was so-called ResNet. So here the initial layers, which if you look at the performance on the ImageNet challenge, the early networks achieved the error around sort of 25% and had, this is for the non-deep networks. Then with the deep networks with about 8 layers, the performance dropped below 15%. Then we had these networks between 19 and 22 layers. And then this last example is this ResNet network, which was introduced in 2015, which had 152 layers. And so what was the idea between the ResNet network? So again, in order to take the sort of push a little bit the observation that the deeper is better, but at the same time have this ability to handle these vanishing gradient problems, the ResNet introduced this idea of so-called skip connections. So you would have an ability to completely skip this block of convolutions and nonlinearities and go directly to the next layer. And then the other idea was that the feature maps from the consecutive layers could be added. And there were 2 ways how you can add the feature maps. One is that if the dimensions of these feature maps between previous layer and next layer are the same, you simply add them. Otherwise, you will use the 1-by-1 convolutions to match the dimensionality of the layers, and then you simply add them afterwards, right? So for example, if you would have, I don't know, 128 channels at the level 5, and you would have 512 channels at the level 6, then you can do the up convolution of the, not up convolution, you can do this 1-by-1 convolution in order to increase the dimensionality of 128 to 512 by basically learning how to combine the 128 channels in order to generate 512 responses of the feature maps. So this was the main idea behind the ResNet. And so after this initial exploration, what has happened was that these ResNet architectures, which were around here, ended up being quite favorable in terms of both the accuracy. So we had high accuracy performance on this ImageNet challenge, but they were also very efficient. And then the size, the radius of the ball is demonstrating the number of parameters which these networks had. So notice that the overall trend was towards increasing the speed, which also was closely related to the reduction of the number of parameters without really sacrificing the performance. Okay, so this is sort of the classification story and a little bit of a history why these different architectures came around and what motivated the progress in this field towards where we are today. So the second problem, which is very relevant and has been sort of considered subsequently, is this problem of object detection, where now we are no longer just tasked to assign a single label to an image, but our job is now to also localize the object in the image. And so now we need to make a prediction of what is the location of the image, which is characterized in terms of X and Y, and also the size of the bounding box, which has a particular width and height. And we'll see a little bit later that the bounding box may not be sort of the best representations of objects in images, but this was sort of definitely the next step, which enabled us to have more accurate predictions. So what are the challenges of object detection? So the first is that image can contain more than one class, and you can also have multiple instances of a particular object per class. So you can have multiple pedestrians, you can have multiple vehicles, you can have different types of cars or bicyclists. So the second job which you have is you care about localizing the bounding box accurately. So the job of these models is going to be to predict the bounding boxes and class labels and the confidence scores. While in the classification case, all we had to do is to predict the confidence score per class, and that was our classification problem. And then we, of course, because we need to localize things, we also have to worry about the false positive. So we need to figure out whether the detection is actually a true detection or whether it is a false positive. So here we'll have to also have a different evaluation methodology, how we are going to score whether a particular example is the correct detection or not. And so the way the evaluation metric, which is being used in the context of these detection tasks, is that if you take a ground truth bounding box, so suppose this is a ground truth bounding box, and if you take the intersection of the ground truth bounding box with the predicted bounding box, and if that intersection divided by union is greater than 0.5, this is considered a correct detection. So if I have this red is the ground truth detection, and suppose that this yellow is the predicted detection, so notice that these two bounding boxes have a large overlap, definitely more than 50%, so this is going to be classified as correct. So this was the evaluation mechanism. And of course, as you can imagine, how well you perform is then a function of this threshold. So typically, when one considers the evaluation of object detection models, one typically evaluates it for different values of the threshold. Okay, so how can we take what we have learned for classification and apply to an object detection problem? And before I proceed, I want you to sort of appreciate the difficulty of the problem. And so one way how you can conceptually think about the object detection problem is in the following way. So you can imagine that you have this window sliding over an image, and at each location you want to evaluate, is the object there or not? Is the object there or not, right? So you, in some sense, want to run this sort of binary or multi-class classification per location, because that's going to determine the location of the object. But on the top of it, you also don't know what the scale of the object is. So whatever window are you sliding, or whatever area are you using to aggregate the features from, is also a parameter. So you have to somehow determine it or sample it, because that's effectively going to determine what is the size of the object you are predicting, and this is something you don't know ahead of time. So the early approaches for these object detections have been, so in order to tackle this task in the supervised setting, now you need different types of data sets, because you need ground truth labels, not only for at the image level, but you need actually ground truth labels at the level of bounding boxes and the locations of the objects and images. So the early data sets for doing so have been sort of developed in early 2000s, and they were sort of quite small. And these are some examples of the ground truth labels for different object categories. And the early, the so-called PASCAL dataset considered only about 20 classes. But it turns out that despite of the fact that the dataset was quite small, some of these early application of these deep convolutional neural networks were already quite successful on this dataset, partly due to the fact that it was possible to pre-train these large networks on the ImageNet dataset. So a lot of the kind of the feature extraction layers did not have to be initialized from scratch on this object detection problem. And then the other data set, which sort of followed up and was developed for sort of benchmarking and evaluating different approaches, the so-called COCO data set, which has about 330,000 objects and 80 object categories. And the total about 1.5 million instances. So this is simply kind of a larger version of the data set, of the object detection data set. So let's have a look how to go about this object detection problem. So we already know that these deep convolutional neural networks are very effective in extracting good features from images, right? So this has been already demonstrated on this ImageNet classification challenge. And there's been a lot of interesting visualizations and introspection done on these networks. So this is something we have already corroborated that this is an effective means how to learn the representation directly from image data. So the first attempt to use these deep convolutional neural networks for object detections were evolving around this idea, well, suppose that I have some mechanism how to generate some proposals or select some regions from the image. And what I'm going to do is I will simply crop these regions. I will resize them to a fixed size, and then I will pass them through my convolutional neural network, right? So this resizing was, however, quite awkward because you can have a region in the image which corresponds to a cowboy, and it is kind of a long and narrow bounding box. But if you want to pass it to a deep convolutional neural network, the structure of the network requires a particular size of the image, and everything has to be resized to the same size, right? So you introduce various warping artifacts in order to be able to use the methodology or the classification pipeline for this detection. And the process of generating these regions was independent, using some bottom-up segmentation techniques developed in computer vision community. But it turns out that even when this was done, it was already very effective. So the network was just used to compute the features. And then you would take the features from the last fully connected layer and simply feed them to support vector machine classifier. And you, even with this just simple strategy, one could achieve 20% increase in the performance compared to the hand engineer methods. So now, what was the problem with this technique? Well, the problem was, the easy thing is that you don't have to do anything. You can take the network pre-trained on the ImageNet and just treat it as a feature extractor and train a sort of classical, commonly used support vector machine classifier. The cons, however, was that it was very slow, because if you had 200 or 1,000 of these region proposals, you would have to run all of them through this network. And the second thing, that it was not sort of fine-tuned in an end-to-end manner. So there were basically these different parts of the pipelines, which all had their separate parameters, and it was sort of hard to select these hyperparameters in the isolation, and it was also very, very slow. So the training took about 84 hours, and it required a lot of disk space. So the next idea in this object detection was to see if we can somehow pass the image through the network only once, right? Because that was the main bottleneck of the previous network. Every proposal had to be passed through the network. And so this was the idea of the so-called fast RCNN, where instead of generating the hypothesis about objects at the level of image, they were actually generated at the level of the feature maps, where different hypotheses about the presence of the object was made, followed by this idea of so-called region of interest pooling, and then subsequent classification. And then it went to the fully connected layers and so forth. So one issue which had to be solved in the context of this object detection was that if you take a bounding box which has a particular size, you need to somehow resize or resample the feature map in a way that at the end, all the feature maps, regardless what size of the bounding box they come from, can be fed into these fully connected layers, because this fully connected layers has some fixed number of parameters. And so this is the idea of so-called regions of interest pooling, where you will simply crop the feature map at the particular, according to the bounding box, which is the proposal which is generated at the feature lab, and then use some interpolation techniques to resample. And then the second component was this idea of reducing the feature map to the size of the fully connected layer. So imagine that if my initial feature map was, I don't know, 2, 6, 8 by 8, but my fully connected layer has only 4 inputs, I need to figure out how to resample this and how to pool. And so the way how this was done is you would simply pool, you would split the bounding box into some number of regions, which would correspond to the ratio of the bounding box and the final size of the layer, and then you would pool according to this region. So here, the black bounding box would correspond to the split of the feature map, and per each quadrant, you would simply take the maximum, and that would be the pooled feature map, which would get connected to the fully connected layer. Okay, so quickly, a couple more things. So what was happening in these networks for object detection was that now, in addition to having only classification loss, we had this additional component, which was the regression loss, which was trying to regress the size of the bounding boxes between the initial proposals, which were the hypotheses generated at the region of, at the sort of last level of the convolutional feature maps, and the actual bounding boxes. So this is how the loss functions look like for the object detection. So this is the traditional softmax loss, and then this was loss associated with the difference between the bounding boxes. And the difference between the bounding boxes, this loss accounted for the error in the location of the bounding box, which was the XY location, and the width and height, right? And the size of the bounding box. So the bounding box parameters, there were 4 parameters, X, Y, width, and height. And this is this part of the loss function was then doing the regression and computing the loss between the predicted bounding boxes and the ground truth bounding boxes. And this already generated sort of significant improvements in speed by 146 times faster than the previous approach. And further advancements have been made in both an accuracy and the speed, is where the mechanism for generating the initial proposals was actually trained using a separate loss, and where the networks were actually sharing the backbone. And this sort of guaranteed that the better proposal bounding boxes were generated, which were then further regressed using the head of the object detection network. And so this architecture was called so-called faster RCNN. So, and again, sort of had the loss were again this multitask loss, because the network was first trying to classify, to detect objects from background, and then the hypothesis which passed the object had a high probability of being objects, were then further classified to being one of the classes. And let me speed up here in order to, in the interest of time. So this is roughly the state of the art of the object detection. And we'll discuss in a little bit more detail on how these models perform on the data sets which are relevant to autonomous driving. I'm going to introduce these data sets next time. So this was more kind of describing the rationale behind these models and what is the state of the art. And I would just quickly, so notice that again, dramatic improvements in performance have been made. So I will briefly sort of skip through variations of these architectures for object detection, such that we can proceed with the last task at our hand, which I wanted to introduce, and this is the problem of the semantic segmentation. So these are sort of some further improvements in both the speed and accuracy, and some variations of the loss functions, which sort of propose different weighting between the positive and negative examples in order to improve the training. Here is some example of how these networks perform in real time. And I will again skip this. So the last problem which I would like to talk briefly is this problem of semantic segmentation. So this is a problem which now, instead of assigning labels to the whole image or assigning labels to the bounding boxes and localizing the bounding boxes, we would like to actually assign a label to every pixel in the image. So this is the class of problems where these convolutional neural networks are used for dense predictions. So you want to basically generate predictions for every pixel in the image. And so the advantages of this are that you can not only explain the objects, but you can also reason about the surroundings of the environment, because you are now have an ability to generate hypotheses for every pixel. For the object detection, the advantage is that you can have more refined models, because bounding box is a very crude model of the object. If you have an object of the shape which does not fit well with the bounding box, you are going to have a lot of pixels which do not belong to the object in the bounding box, and this is sort of detrimental of the accuracy. So notice that what you can actually strive for is to have these very detailed boundaries of the objects. And here, this would be an example of these models applied to scene understanding. So in the context of autonomous driving, you can apply these models to be able to predict lots of things about the scenes. You can predict where the parking spaces are, where the lights are, where the trees are, where the buildings are. So it's applicable also to these non-object categories. Okay, so this is so we are basically looking at the models which will be able to do per pixel prediction. And so the main idea between these classes of models, and this was also already introduced partly in the classification architectures, is this idea of these fully convolutional neural networks. So, so the idea behind the fully convolutional neural networks is the following. So for the classification, when suppose that this was the last convolutional feature map, this was typically followed by these 4 fully connected layers, and then at the end you would get a prediction where the prediction would be a vector where the probability of the class, which is the most likely, will be the highest, and then you would have some predictions for other classes as well. So now, instead of sort of considering these fully connected layers, which we also discussed carry a lot of parameters, imagine the scenario that you will take the last convolutional layers, and then these layers have a very low resolution, but they can make some predictions which have some spatial support. So what you can do is you can take these last feature maps and actually apply these one-by-one convolutions to learn the per class prediction from these last feature maps, from the lowest resolutions of the feature maps. So what will happen is that you will obtain something like this. So suppose that you will consider the lowest feature map has some resolution of, well, suppose that this is some lower resolution, some H bar and W bar, and then you're going to follow it by one convolutions where you will learn how to basically match the dimensionality of the feature map where the spatial support is the same, but now the number of channels corresponds to the number of classes. So you will basically generate a per class spatial predictions of these maps. So this was the first idea, and here are some examples of how these predictions look like if you simply would make the predictions from the lowest convolutional feature map, which was sort of subsampled by the factor of 32 of the original image. And you can see that the predictions are very blurry. So the second part of this pixel-to-pixel predictions was trying to figure out how to get the resolution back. And there were 2 main strategies how to do that. One is just a simple linear upsampling or up convolution, and the other one was this idea of so-called dilated convolution. And this basically led to the following class of architectures. So you would have, the architecture would have this U shape where in the encoder part of the architecture, the resolution of the feature maps would be decreasing, and then you would learn how to increase the resolution of the feature maps. And this was done using this idea of upsampling or dilated convolutions. So what you do is you will take the low resolution feature maps, you will pad it with zeros, and then you will learn the filter how to fill in the zeros in order to fill the values in the most informative way. And this most informative way also corresponded to this idea is that when you are learning how to upsample, you also want to use the information from the high resolution channels early in the architecture, so these architectures typically introduce these so-called skipped connections, such that you can simply add the features from the earlier feature maps where you are together with the ones you are using for the up convolution. And there are also a lot of nuances. So I discussed the issue of up convolution. Another nuance is how to handle the unpooling information, because the pooling simply takes some maximum over the region, and you need to actually remember where that maximum came from in order to do the unpooling correctly. So here are some ideas. Here is some visualization how this consecutive deconvolution, unpooling, and deconvolution works. So this is the prediction of the bicycle at the level of spatial resolution, which is 14 by 14. Then if we do unpooling, we are gonna double the resolution and simply copy the high activation values to the right locations, and then we learn how to upconvolve. And then if you do it a couple consecutive times, you can get the predictions at the level of the original resolution of the image.
Yeah, we have a question from Darius.
Yes.
Unmute you, Darius.
Yes.
One simple question. If you do this downsampling, at one point, the network decides basically what's the best explanation for the region. But it could be that there are multiple objects which are very similar. So the network will decide it's a bike, but it could be something, well, I don't know what else has wheels. It could be something else, but this information will not be propagated anymore. The decision is made in the network. So is there a way to actually get multiple alternatives? What is in this region? Or will the network just say, well, it's a bike, because at the lightning I was having, it's basically the best match. Do you understand what I'm trying to say?
Well, so this is sort of related to a couple of issues. One is, so what you get out of the network is this. So you will basically get, I'm trying to find the right picture. So what you will get is, if you have C classes, you will get per location probability that the object is of a particular class, right? So if you have some ambiguity, then you can work a little bit with the class prediction probabilities which you have per object class, right? Mm-hmm. Because this going from this per class probability, just going to taking the maximum, you are going to lose that ambiguity information. So this is one component. Yeah. The other component, which I will discuss a little bit next time, is this idea that, so this network, this type of architectures essentially just do per pixel prediction, and it's like taking a little window neighborhood, computing some feature statistics and doing a per pixel prediction. So one problem with these architectures is that they cannot properly disambiguate between different instances of the objects of even the same category. And I will talk about it a little bit next time of what are the strategies, how to tackle it. And let me actually introduce it right now, because I think we are slowly running out of time. So I want to kind of just briefly leave you with the idea is that there are several ideas out there how to handle this upsampling and deconvolution and unpooling. And they're sort of use either this idea of unpooling and upsampling, or they use this idea of so-called dilated convolutions. They typically have these skip layers in order to reuse the features from early layers. And here are just some references of the top performing architectures. But this is to return to question what Darius mentioned, is that to understand this relationship between object detection and semantic segmentation, you have to realize that the object detection gives me bounding boxes. The semantic segmentation is going to give me per pixel labels. But the semantic segmentation alone is not going to tell me that I have 5 people there. It's just going to tell me these pixels are labeled as people, right? And so some of these follow-up models try to tackle this problem of so-called instance segmentation, which is sort of somewhere between the initial detection models and the segmentation, where you can exactly segment the multiple instances of the same person, even when they're overlapping. And, you can count them, you can sort of classify them and so forth. So what I will talk about next time is an extension of this model, which is called so-called PASCAL CNN, which does both the detection and segmentation and can generate really impressive results. And then I'll talk, so these pixel-to-pixel models are applicable to other problems than predicting the semantic labels. One commonly used problem is ability to predict depth per pixel. And I will touch up on that in the next lecture. So I think this is where I will finish. I believe that's all what I have today. And tomorrow so this is basically, we have introduced the models for figuring out what are the instances of semantic categories of interest. We can label the background and understand, whether we are in the urban area or whether we are in the countryside. And what we are going to talk about next time is some of the 3D perception and a little bit more details also how to improve these object detection models. And the last thing what I'm going to do is I'm going to introduce a lot of these problems and the data sets which are currently being used for autonomous driving to evaluate the accuracy of these models on some data sets, and then we can discuss some challenges and drawbacks of this methodology. So this is what we're going to talk about next time. We will talk about how to recover 3D, we'll talk about how to recover pose, and then some perception action loops.